Okay, this is video lecture number 2. Starting at the bottom of page 59 in the Monahan-Walker book, the authors introduce 3 possible goals of this empirical approach to science. All of these goals are related to finding causal relationships, right? Related to cause and effect. And the 3 goals as set forth by the authors are number 1, understanding, number 2, prediction, and number 3, control. And we're going to go through each of these in turn. So starting here with understanding. Now understanding or explanation, right, involves the search for the causal mechanisms or the processes by which something operates and changes. So how do we define cause and effect? How do we know that something is the cause of a particular effect? And I have on here a good and simple explanation. I think this is originally from John Stuart Mills, that defines what you have to see before you can confidently make a scientific statement about cause and effect. So a causal relationship can be said to exist if, number 1, the cause preceded the effect. Of course, that makes sense. The cause has to happen before the effect happens. Number 2, you have to know that the cause was related to the effect. And number 3, if you really want to make a clear causal connection, you have to make sure that there aren't any other plausible alternative explanations for the effect that you're seeing other than the cause that you want to be able to attribute it to. Now, in real life practice, true experiments are probably the only perfectly pure method particularly well suited to the identification of clear cause and effect, because in a true experiment we have some advantages. We can do 3 really important things. Number 1, we can manipulate the presumed cause and then observe the outcome afterwards. Number 2, we can also see in a true experiment whether variation in the cause is related to variation in the effect. So for example, if you're studying a particular chemical and you want to figure out if it's a carcinogen, if it causes cancer or not, and you're studying rats, you might want to vary the rat's exposure to that carcinogen to see, for example, whether rats exposed to a higher dose of that carcinogen or potential carcinogen develop cancer sooner or develop a more severe form of cancer, so that when you're varying the cause, it causes a variation in the effect. Okay, and then the last advantage of a true experiment is then you can try to use various methods during your experiment to reduce the plausibility of those other possible explanations for the effect. Okay, and this is one of a number of ways scientists can try to control for what we refer to as confounding variables or confounds. And you can try to control for those as a scientist by designing experimental methods that purposely minimize those confounds. Also, though, you can use some statistical methods and apply those during the phase of analyzing your data that you got from your experiment. You can use those statistical methods to minimize the effects of any extraneous uncontrollable factors that you can't rule out. One that is pretty commonly used that you might have heard of is multiple regression. Some of you might know about this. Most of you have probably heard of it, at least in passing. Multiple regression is a method that can increase your confidence as a scientist that the effect you're seeing is actually being caused by the factor that you are mainly interested in. So generally, in science, there are a variety of methods of greater and lesser strength. Some are going to have more power in some respects. Others have more power in alternative respects, right? And that is why we like to approach things from a number of different aspects and hope for that convergent validity in our results. The last thing on this slide that I want to make sure to point out here is down here. The book has a short piece on causal relationships, some sort of categories of causal relationships, necessary relationships versus sufficient, right? Necessary versus sufficient causes, contributory causes, and feedback loops, and other causal chains. And you should take a look at those pretty closely there in the book on page 60 and be familiar with those concepts. They're not very difficult. For example, a necessary cause, but not a sufficient cause, of passing this class will be writing the required memo, right? You cannot pass without writing the memo, so it is a necessary cause of passing the class, but writing it alone isn't going to guarantee passing, i.e. it is not a sufficient cause all by itself for passing. Flipping that around, if we want to think of something that is a sufficient cause but not a necessary cause, how about stopping on the road, stopping your car on the road? So a sufficient but not necessary cause of stopping on the road might be running out of gas, right? Running out of gas is certainly a sufficient reason for stopping on the road, but because there are other possible things that could cause this, like approaching a red light or approaching a railroad crossing gate that's down. Because of that, running out of gas, of course, is not a necessary cause for stopping on a road. And then, as you saw in the book, contributory causes are, of course, by definition, not sufficient and not necessary, but instead they just can be thought of as contributing to the occurrence of a particular phenomenon. All right, next I want to define a couple other terms that we hear a lot when we're talking about science, and that is theories versus hypotheses. Now, these terms are often used interchangeably by people talking about cause and effect in science, but really theories are more comprehensive explanations of a cause and effect relationship, whereas hypotheses typically speak to the relationships between more discrete, specific variables. And in fact, theories are usually said to be the generators of hypotheses, right? And so you have a theory, you generate a hypothesis, and then it's the hypothesis itself that is the thing that gets tested. So it's hypotheses that are testable or verifiable. And then in the end, you might end up with a set of interrelated hypotheses that if you take them together, they can form a theory and support that theory as long as any of the hypotheses that are necessary for that theory are not successfully falsified by some experiment. So we could say that a good potential theory is always going to yield hypotheses that can be tested or verified. And of course, the other side of that same coin, you want to generate hypotheses that cannot be found to be false over time through doing good hypothesis testing. And so that's a good potential theory. On the other hand, we'd say a faulty theory is one that yields hypotheses that can't be tested, or in fact that yields contradictory hypotheses. There are a lot of diagrams out there illustrating the interplay between hypothesis and theory. This one just illustrates all the hypothesis testing that has to be done before something gets elevated to the status of a theory. So you go around and test and test and test until you can use that hypothesis to support your theory. Now, getting back to our Huxley quote that we had in the first class about science being nothing but organized common sense, of course, science begins in much the same way common sense observations might begin, right? We observe some phenomena. By observing a phenomena, scientists might formulate theories and hypotheses that explain cause and effect relationships, or that just describe some phenomenon of interest. But right there is where science departs from common sense, right? Because science then goes on to subject its hypotheses to rigorous testing. Now, we always have to remember this truism that's on the slide here, that no hypothesis actually can be proven to be true. No hypothesis can actually be proven to be true. This idea is often illustrated using philosopher Karl Popper's explanation of falsifiability, and he used this example of swans. So he's very famous for this white swan, black swan concept. So starting with an observation here, you might observe a large group of white swans, or over time you may even see group after group after group of all white swans. So you might come up with a hypothesis here that all swans are white. But you can never, ever definitely prove this hypothesis, right? You can certainly corroborate your hypothesis by the experience of observing 500 or 1,000 or 10,000 or 100,000 swans, all of which are white. And the more white swans and only white swans that you observe, right, by replicating this looking for swans task, the more confident you might be that you've verified your hypothesis that all swans are white, since in fact you've failed to falsify it. But the fact does remain that no matter how many white swans you count, there always remains the possibility of a black swan lurking somewhere out there. And looking for black swans illustrates this fundamental principle of the scientific method. Scientists have to make an effort to disprove or falsify their own hypothesis. So hypothesis testing, to use a sports or military lingo here, is hypothesis testing really is the playing field. To use the sports metaphor, hypothesis testing is the battleground, to use the military term, the battleground of science. I also have in this PowerPoint, as you can see, a couple of much more complicated diagrams that illustrate theories and hypothesis testing. If you want to stop the recording and take a look at them, this is just to show you all of the various diagrams there are out there. This one is a little bit simpler. You have your observation here, right? You come up with a hypothesis that might explain that observation, and then you go down here and you test it, right? And you keep testing it and testing it and testing it. And as long as you don't fail, right? If you keep testing it and your hypothesis holds true, and that happens many times, then the hypothesis can be held up as support for a particular theory. Of course, if any time in this process your hypothesis testing fails and you actually falsify your hypothesis, now you have to go back up here and start again by coming up with a new hypothesis that explains your observation. Okay, so the second goal of the empirical approach that's mentioned in the book is this idea of prediction. Obviously, prediction is the ability to say what will happen before it happens, right? So prediction is actually a component of all sciences, and I have some slides to illustrate that. One of the very earliest forms of science, right? Early astronomy tried to predict the movement of the stars. How about meteorology? Meteorology is really an applied science, a form of applied physics, and that, of course, predicts the weather. Seismology, for example, the study of earthquakes, is trying to work on methods to predict earthquakes. No really strong tools yet developed for predicting earthquakes, but certainly that is a goal of seismologists. Here we have a picture of Pavlov, a famous scientist. You might be familiar with his work with dogs. He predicted when his famous dogs would salivate, in fact, after conditioning them to expect food when a bell rang. I'll give you a minute to read this cartoon. His dog was turning the tables on Pavlov in this cartoon. Skinner is another scientist who used animals. Skinner used rats, and he tried to predict when rats would press on bars in their cages, trained them to do so. And an example that we've already talked about in class, psychiatrists, of course, are asked by the law to predict whether people will be violent or sexually violent in the future. But remember that prediction, interestingly enough, is not dependent necessarily on causation. Prediction is not dependent on knowing causation. Now, the book actually gives a great example of the correlation between ice cream consumption at the beach and drownings. Ice cream consumption at the beach and drownings appear to be correlated, right? The more ice cream that is sold, the more people drown. Eating ice cream itself does not cause drowning, despite the fact that moms everywhere make their kids wait after eating to go swimming, right? But both these things, consumption of ice cream and drownings, are affected, in fact, by a third variable, which is temperature, right? When it's hotter, more people buy and eat ice cream, more people go swimming. So both of those things, in fact, are affected by a third variable. The other interesting example in the book is scurvy, the disease of scurvy, which we now know is caused by a lack of vitamin C. But the actuaries in the British Navy in the 1800s noticed that scurvy was in fact rare and even non-existent on ships that had been loaded with citrus fruit before the ship sailed. So what those actuaries could actually do is predict more scurvy on no citrus ships. And of course, they had no idea what the actual biological mechanism was. They might have had some limited causation information, i.e. something about the lack of citrus fruit might cause or contribute to developing scurvy, but they didn't have the actual understanding. And I just figured out teaching this class that in fact this is why British sailors were called limeys, because they used to load these limes on the ships. But again, this goal of prediction is not necessarily dependent on knowing exactly what's going on with causation. Okay, this is the end of video lecture 2.